This laboratory will start out where the last one left off on AM modulation. We will start with our AM modulator. When we turn on the scope and generator, we see typically this blank screen on the scope generator. We'll set the generator for 1 megahertz. So under frequency, 1 megahertz for our carrier. We will then set up the modulation. We'll go with the default modulation, which is 100 hertz. Actually, let's change that frequency to be 1 kilohertz. More reasonable. And the AM shape will be sinusoid. And the depth of modulation, which is the MA value, is 100%. Now we are ready to energize the unit, so we turn on the output. We're going over to the scope. We can push the auto button and we see the signal. It is very typical with AM signals to get a good display. That's because the waveform is changing voltage all the time. And that is confusing to the scope. Now if I zoom in on the time base, you can start to see our typical AM waveform. But it is clearly not triggered properly. By far the easiest way to deal with this situation is to use a regular triggering signal. So let's look at that possibility. Every signal generator has 2 outputs. One is the typical standard output, which is creating our AM signal, and above it is a sync or synchronization signal. This signal is simply a square wave at the frequency of the generator, which in this case is 1 megahertz from our sine wave, original sine wave. So I've connected that up to the scope. Now let's run the auto scale here. And we see the typical display. Again, the AM signal being a little jumpy again. Now, the square wave, which is at 1 megahertz, from the sync signal, we will use that for our trigger. So simply select menu under the trigger selection and then select channel 2 as your reference for the triggering. Now that doesn't solve the problem because the trigger is still trying to trigger at 0 volts, which is not a single repetitive point. So we will now go to edge and go to pulse triggering. Once we select pulse triggering, the standard signal and rise time of the scope will set up the pulse. Now we have a nicely triggered signal. Now I'm going to change the input to move the sync signal over to the external input. That is the standard setup. So from the sync signal, we go to the external input. We adjust the triggering, press the menu button, and then the adjustment on the channel to be external. Now as soon as we select external, the pulse signal or the square wave sync signal is now the trigger. And so since that is a standard repetitive square wave, it is easy to trigger on, and I see my modulation, my AM modulation signal. And you can go back and change any values you want on the modulation. You can change the frequency. 1 kilohertz is our frequency. We can change it to be 2 kilohertz. And of course we see the change. We can change the depth of modulation, which is the MA value. If I change the depth of that value, 100%, 90%, 80%, I'm actually changing the EM value, or the modulation voltage. I can also change the shape of the signal. I can change it from sine to square to triangle. All of those are selections that I have available to me. I'll return it to the shape of a sine wave and the modulation index of 100%, since that's a known type signal. Now we are ready to look at the demodulation of this AM signal. So the initial setup is quite simple. The input signal from the AM generator goes into the diode and, in this case, a 1K ohm resistor. The output is being measured across the resistor, so we should see the half-wave rectified type signal. And indeed we do see that signal. I will reposition that unit so it's in the middle of the screen, or at least convenient to look at. We'll change the magnitude. If I zoom in on the signal, you will actually see the individual 1 megahertz pulses being rectified. There's a little capacitive effect that you'll see in that time shift. If I change the modulation level, you will see a change in the signal, in depth of modulation. Now I've reconnected the ground to be the ground on the capacitor. So now the capacitor box is in the circuit in parallel with the 1K ohm resistor. I've got it set at the smallest value, which is 0.1 nanofarads, so 100 picofarads, and we see the waveform has not changed significantly. Now I will increase the value, which is the filtering of that signal. So I'm going to increase from 100 picofarads all the way up towards 0.22 microfarads. As we adjust it, we start to see the filtering take effect on the demodulated signal. I'll zoom in here just so we can see what is happening, but you can see that now we get the classic capacitive discharge. I'll change the value to show that smaller capacitors give a shorter discharging time. And I'll zoom back out so we can see the signal. Now, when I increase the capacitor, eventually I'll get the envelope of the original AM signal. And we see this as the sine wave. Now there's a little distortion because as I come down to almost 0 volts, the diode cannot turn on, and so it goes flat. We can modify that by changing the depth of modulation to be something lower than 100%. So in this case, I'm now at 30%, and I get a nice sine wave demodulation. Increasing the capacitor won't really affect that signal unless it gets too large. Now, to prove the demodulation of that signal, I simply go to the AM shape. In this case, I will change to a triangle wave. And I see that the triangle of the envelope now becomes the triangle of the demodulated signal. So the envelope becomes our signal after the diode rectifier and filtering. And now we can run this to our audio amplifier, because this is now at 1 kilohertz, our modulation frequency, and that is essentially our diode detector demodulator. Changing to a square wave, I'll see the change also. You can see there's a little distortion on the time, but that's not going to be significant for our case. Back to a sine wave, if we look at that. Now, one thing you will notice, the signal is shifted by a certain DC level, because the diode cannot reverse bias and carry the AC signal, so there's always a bias associated with that signal. Now that bias is actually associated with the carrier. If I go back and set the AM depth to be 0, we will see that I have a DC signal on my demodulated content, because this AC modulated signal is just being rectified. Now that actually turns out to be a very important aspect of the diode detector that we will talk about later in automatic gain control. Increasing the modulation depth again back up to something reasonable, as long as we don't get too close to 0 volts where the diode will turn off. It looks like a good demodulation. As a quick modification of the circuit, I have reversed the diode. Now, of course, that reverses the half-wave rectified signal. And when I look on the scope, I now see that the ground or 0 point is at the top and the signal is negative. So that negative voltage associated with the carrier can be used as our AGC signal. Minor point, but it can be significant in the design of your receiver. Now I've changed the diode to be a germanium diode. Now remember, germanium diodes have a forward voltage of only 0.2 volts. The value of being able to use a germanium diode is if I increase the modulation index, I can go to a much larger value because it takes minimal voltage to turn on the diode. So now that's 100% modulation, but we get a good looking sine wave even at 70-60% of modulation. So the diode, the capacitor all determine the aspect of the demodulated signal.